Thanks a lot to the organizers of this meeting for the late celebration of Julia's 70th birthday. And so this is a work that I've done in collaboration with Matthäus Pavler, who is here and who is working now at KTH, and Luca Vitale. So the idea is to try to find express from theoretical reasoning the breakup rate of particles in turbulent flows. So more than particles, these are aggregates, and so the breakup word is a very large engineering and physical subject, and it deals with industrial colloids. So colloids are material in which you have a continuous phase and then a discrete phase, and they can be liquid or solid or gas. But we will mostly have in mind liquid colloidal solutions. And then there are also applications from nanoparticle powder manufacturing, and there can be some relevance also for the breakup of liquid droplets in atmospheric flows, and then it's of interest also the problem for particular matter in other environmental systems, such as the marine snow.
What is marine snow?
Marine snow is small animals or small objects that you have in
if they die, they sediment.
sink.
Okay.
And from an industrial point of view, the interest is in trying to build up mixing or demixing devices. That is, to build up devices in which, helped by the flow, you can either perfectly mix the discrete phase with the continuous phase, or in the opposite direction, you want to separate them. The framework in which we are working is that considering neutrally buoyant aggregates that are very small, so they follow fluid streamlines, and because they are very small, also we can consider them as point-like objects, so we don't have to worry of their size in terms of physical description and in numerical simulation, and also from finite size effect. And the idea that we have is that this object can break in turbulent flows because of local shear stress that become high enough to break up, so to overcome the aggregate strength or the surface tension forces if we're dealing with liquid particles. And we will just consider breakup due to local shear stress and not other mechanisms. And so if one tries to deal with a complete problem, what you want to study is the probability density function of the aggregate of a given mass, the theory psi, depending on space, depending on the flow conditions, and on time, really. And this is a Boltzmann-like equation that is generally called population balance equation, in which you have the time evolution, then you have transport, then you have this term that is related to the force acting on particles, and then you have other terms which express so particle breakup, particle reaggregation, if they can coalesce, and also you can have terms of particle collisions that do not give rise to coalescence. And this is not to mention that you can also have other effects like evaporation or condensation that we are not considering. So this is a very complex equation, and generally these degrees of freedom, spatial and advection, are averaged out. So then one is only interested in the time evolution of the probability density function of aggregates of a given mass. That is what we will So before showing what we have measured, so if you limit now just to the breakup problem, that is, we are not now considering the reaggregation, and if you have averaged out the spatial and velocity degrees of freedom, you end up with a very simple equation in which you have the breakup rate appearing in the time evolution of the aggregate mass distribution. And so this is the framework we are now considering. We are considering that reaggregation is neglected, and we are considering that aggregates of larger mass that created mass C are also neglected, and also we consider that breakup is instantaneous. That is, as soon as an aggregate of a given mass feels along this particle, along this Lagrangian motion, a local shear stress that exceeds a certain critical value, it breaks. And the critical value is related to the mass of the aggregate with a power law, with an exponent larger than 1. And so the idea is that large mass can break up very easily, while small aggregates needs much higher local shear stress to break up, which is a very physical idea. So how do you imagine you are now performing an experiment? So you have a flow, turbulent flow, with a non-trivial distribution of local shear stress, which is far from Gaussian distribution. And now you see the flow with aggregates, and our working hypothesis is that the aggregates at the initial time are in a position of local shear stress that is smaller than the critical one. So how do you measure the aggregate breakup rate? So there are two quite natural ways to do it. So this is a time plot of the value of the shear stress along the aggregate trajectory. So this is time, and this is the aggregate that initial time feels shear stress that is smaller than the critical one. So you can measure breakup rate in two ways. You can measure the time it takes, the average time it takes for the aggregate to feel the critical shear stress, and this is this time tau here in this plot, and then you can clearly average over many trajectories. And or you can measure the breakup rate in another way. You can count the average time that the aggregate spends below the critical thresholds. The inverse of these two average time gives you can give you the aggregate breakup rate. So this is somehow this is the first exit time measurement. So it's the first time the aggregate fills the and the other, we call it diving time. So let's see what we obtain when we measure these two times. So the first measurement is the breakup rate from this inverse of the mean exit time that is clearly given by the exit time distribution of the local shear stress along the Lagrangian trajectories, and this is clearly a Lagrangian measure because you have to follow trajectories and then wait the time of the first of the trespassing of this threshold. While the other one, the mean diving time, can indeed be expressed in terms of only Eulerian measurements. And this is something that was proposed by Lachenov in the 80s, and it's just a reformulation of what is called the Rice formula, that is the estimate of the number of up-crossing for stationary stochastic signals. And it can be expressed, and when the observable is the local shear stress, this mean diving time can be expressed in this way. It's the ratio of the integral of the joint distribution of the critical shear stress with its time derivative, averaged over also the time derivative itself, because you are measuring the way the threshold is trespassed, and then this is averaged with the distribution of the critical shear stress from 0 value to the critical one. And this clearly gives you the idea that when the critical shear stress becomes very small, these two terms have to go to 0, but in the same way, so to keep a finite.
If you go out of the presentation and you go into
Yeah, exactly.
The other one.
No, this case.
Oh.
Okay, so this is the way we want to estimate the aggregate breakup rate, and then we want to compare these two measurements. So one is, as I told you, a Lagrangian measurement, and the other one is fully determined by the Eulerian distribution of the shear stress in the field and its time derivative. So once you have these two expressions, you can also try, particularly for the Eulerian estimate, to close it in a simple way, since the joint distribution of the local shear stress and its time derivative is not very easy to obtain in an experiment. And there are two models that we want to discuss. One is to close this, the numerator of this expression. One is just a dimensional estimate, in which you say that the joint distribution is just given by the distribution of the energy dissipations times the derivative of the energy dissipation just expressed by its dimensional value in a turbulent flow. And so this is a very simple way to express this Eulerian estimate. And then there is another model that has been proposed in the past, and in this model, it's not only the energy dissipation at the critical value which matters, but all the energy dissipation larger than it that matters for the breakup of an aggregate at that value of the shear stress. So how did we measure these quantities? We had a numerical simulation of tracers dispersed in a turbulent flow, and we have two different simulations with a different Reynolds number. But today I will only show results for this value. And we also followed heavy particles, but today I will discuss only the behavior of tracers particle and not of particles with inertia. For particle with inertia, the situation is more complex because there is not only breakup due to the local shear stress, but also to the drag stress that is felt by the particles. Oh, by the way, this is the distribution of the energy dissipation in our turbulent flow. Okay, so here comes the result. So here you have the breakup rate normalized by the Kolmogorov time scale of the flow. And here instead of expressing the breakup rate for masses, we expressed it in terms of the critical value of the energy dissipation. And so the black curve is the Eulerian Login-of-Rice expression. And so you see that, as I was mentioning before, at very large, for very large values of the critical energy dissipation, that means small mass, the breakup rate is very small, so it's very difficult to break them. While when we go to very small local shear stress that are related to large aggregates, it's very easy to break up them, and the aggregate and the breakup rate assumes almost a power law behavior. And the blue dots here are the exit time measurements, so from the inverse of the mean exit time. And well, here from the graph you cannot distinguish, but these two measurements are not exactly the same. And indeed it can be shown that the exit time measurements is related to the ratio of the second moment of the Eulerian diving time divided by the first moment. And so what we have here in this graph, we also have two other curves that I want to discuss, and these are the curves that you obtain by closing the Login-of Eulerian estimate by the dimensional expression, so by just separating the joint distribution of the local shear stress and its time derivative by the dimensional measure, and the other model that is the engulfment. As you see, so the dimensional closure and the engulfment model are very good for very large shear stress, but they both fail when we consider events, when we consider the breakup of large aggregates. And as we will see in 2 slides, this is very critical to obtain a stationary state for the size distribution of aggregate in the flow. And so what I just wanted to also to emphasize, this is the joint distribution of epsilon and its time derivative, and this is the dimensional estimate. So you see that it's a very crude estimation of what. So these two quantities are clearly correlated, but not. But the dimensional estimate loses lots of details of what's really happening. And just to highlight what are the difference between the closures and the true Eulerian measurements, so the true Eulerian measurements from the Login-of-Rice expression, is you can understand them when you consider just the numerator of these breakup rates, and this is the true. Black line is the true Login-of expression. This pink boxes are the dimensional estimate, and the red curve is the engulfment model. So you see the engulfment model clearly doesn't work at these small values of the energy, local energies of the local critical shear stress, just because it considers that the breakup rate would saturate for any value. While the dimensional model just fails in considering these very small events. So now you can put up these breakup rate functions in the Smolukowski equation for the time evolution of the aggregate size, and then so which is our balance population balance equation averaged out on space. And so you have 3 terms. 2 terms are related to the aggregation of these particles, and 1 to the breakup. 1 to the breakup, and to the breakup of particles into smaller pieces. And for the aggregation, we use the Safman-Turner kernel, modified by the fact that our aggregates do not have do not fill the volume completely, so they have some fractal dimension. The dependence from the radius to the volume is in terms of a fractal dimension. And then we consider only fragmentation into binary process, that is only aggregate can break in 2 pieces of equal mass. So once we have all these features, we put them together and study which is the time evolution of the aggregate size distribution or mass distribution. And so a way to express this is to consider an observable that is easily accessible in experiments, and this is the volume-weighted mean aggregate mass, which is related to the square of the aggregate volume, and then consider its time evolution. So this is also called the zero-angle scattering intensity, and so this is its evolution as a function of the normalized time for different values of the solid volume fraction, which is the control parameter in this problem. And we consider so the behavior with a true Eulerian fragmentation rate expression, so the Login-of-Rice expression, with the dimensional closure and engulfment. So these curves are, they are just shifted, but this refers to very small initial distribution of aggregates, and going up, we are considering higher solid volume fraction. So you see that both the Login-of and the engulfment model always give rise to the stationary state distribution of the aggregate size, even if the engulfment model can underestimate which is the value of the stationary state distribution, while the dimensional closure clearly fails in this regime for very high solid volume fraction. And so this is just because the events at a very small critical shear stress are underestimated. And so we don't reach a stationary state, but we have what is called in jargon adgelation, which is all the particles trying to just coalesce together, and they form just a unique aggregate. And this the stationary distribution of aggregate size can also be studied. We can study its time evolution, and just still at different values of the volume, solid volume fraction. And what we see is that at increasing the solid volume fraction, we have a broader and broader distribution that is formed, and so we are approaching the limit in which the fragmentation rate has this power law behavior. So that's almost all I want to say. So we have introduced an operational way to estimate fragmentation rate, and so instead of studying the way aggregates break up and then extract the fragmentation rate from fits, what we have done is trying to define a way precise way in which the fragmentation rate can be estimated either from following Lagrangian trajectories or from an O'Larian estimate, and it's what is critical in all this story is the estimate of these events, and this clearly leads to the idea that simple closure also with the normal distribution for the local shear stress are not sufficiently adequate to reproduce what is happening, and if these events are neglected, the stationary state that is obtained for the aggregate size distribution is completely wrong. And then we are now trying to study what changes if we consider inertial aggregates, and also what changes if we, instead of working with the Smoluchowski equation, that is just a posteriori working with a size distribution of the aggregate, really put them in the flow and study the way they break because of real local fluctuation of the shear stress. Thanks.
John, you have a question?
Me?
I thought.
Oh, sure, yeah. So the model for maximum shear stress that is a power law.
Yes.
I don't see how, well, just your main figure, so just you go back to your main figure. This, how does, I mean, that's clearly material dependent. So I mean, you have the right size dependence because the maximum shear stress actually goes to zero as the particle becomes small, no matter what the particle is made of. But I don't see how the material dependence comes into this. And then when you use the
it's not here. It's not present indeed, because here you just put the dependence on the local shear stress.
right.
So then you have,
So then you won't get one curve because each material may have different factor and power law. Okay, so that's fine. So then you.
but once you have the dependency on the local shear stress, then you can adapt to different materials. And
so did you do any of that in your? I mean, did you look at the difference between lead and colloidal particles?
no, what we no, what we just so what's here interesting is that compared to laminar flows where you have just one value of the shear stress, and so you would have in this hypothesis of instantaneous breakup, you would just have a step function. So either you break or you don't break. Here in the turbulent flow, you have all these. Yes, you have a distribution of the shear stresses.
But then when you did the Staffman-Turner closure, you modified it with the fractal dimension, then that will change the power law assumption for the maximum shear stress.
So the fractal dimension of the object is also related to the exponent that we use clearly. Yes, so it changes. So also the way the stationary states approach change.
I have one minute. In the rice trick, you actually calculated the average lifetime. Right?
Means that
It's the first passage time question.
so this is an estimate of the number of up-crossing events.
Yes.
So the number of events that trespass the thresholds from below.
Right. And you calculate the average number of them, right?
Yes.
Can you calculate the whole PDF using the rice trick?
Calculate. I mean, we can do it numerically, but I don't think that there is the
No,
expression.
There is another thing.
Not only for the first moment, you see, for all the distribution.
But
No,
you can,
no, I mean analytically, not from T2. It gives us only with the first moment.
No, I'm not aware of a result
we do
for
more.
all the moments.
Sandra, you can do more. There is some, if you're interested in very high levels, and you want to know what is the probability that it will not, in a huge interval, it will never exceed a certain value. The crossing, you can then relate the probability to the mean of crossing by a Poisson-type formula. It's an asymptotic evaluation. So you can get this. It was not by Eric, myself, Burbatov, and Todd in a paper on Böhmens in the 1997 or so.
Yeah.
So it comes only for the mean number of upcrossing events.
Excellent. So let's thanks to the